All right, class. So today we're going to be doing the 4.1.1 study, and I will be posting this to YouTube, where you should be watching it right now. And what I can do is I will be filling this out. Actually, I have this one pre-filled out, and I will be talking and reading the 4.1.1 study that you can access on Apex. And this is the study guide that will go along with it. Now, we'll have a link to the blank study guide on the team's website, so you can access it there. Also, you can get it through the link in the 4.1.1 study. So let's get started. A meteorologist is a scientist who studies the atmosphere in order to predict the weather and learn about global climate change. Like all scientists, meteorologists gather data to form conclusions. Some meteorologists you do this using giant water balloons filled with helium that carry instruments high into the atmosphere. Now, as an amateur meteorologist, you too will examine each layer of the atmosphere. Your mission: find out why clouds move across the sky rather than disappearing into space. Find out why airplanes cruise at altitudes of around 30,000 feet, and why anxious space travelers in science fiction movies always are worried about burning up when they re enter the Earth's atmosphere. Don't worry, it's a piece of cake. Page 2. Scientists often create models to explain different phenomena. One way to model the atmosphere is as a giant translucent layer cake. The layers of this atmosphere cake are made of gases and are held together by gravity. The whole thing is baked with the energy of the sun. The temperature of Earth's atmosphere also varies with altitude. Each layer's temperature depends on what kinds of gases are in the layer and whether those gases trap solar radiation, which is light energy from the sun. But air is just air, right? Wrong. Nitrogen, N2, is the most abundant gas in the atmosphere, followed by oxygen, O2. There's also water, vapor, H2O, trace amounts of carbon dioxide, CO2, argon, Ar, helium, He, neon, Ne, hydrogen, H, methane, CH4, and even krypton, Kr. So on the bottom of this page, there is a table which tells you a little bit about each layer, how far it is up, what the temperature is like when you go up and down in that layer, and special qualities the layer has. So I have filled in already the study guide, and I filled in all these bits. And what I'll do is each page coming up talks about each one of these layers. So I will kind of zoom in on each one of those layers on the study guide as I talk about them. But here's your first thing to fill out: the composition and factors affecting temperature. So composition, I just told you, is all those different gases that I have written down. And then factors affecting temperature, things like altitude, what gases are in an area, and how the gases trap heat. Remember, anytime you can pause it and write these things down if I'm going too fast. So let's go to page 3. Traveling in style. Hot air balloons have been used since the 18th century to probe the Earth's atmosphere. Early flights carried curious scientists in the upper troposphere. Sometimes they flew so high they passed out from lack of oxygen. In the first part of your mission, you'll explore the troposphere in a hot air balloon. As you climb higher and higher, it'll get harder and harder to breathe. You'll feel colder as you float up. You might even get rained on. But no matter how hard you try, your hot air balloon won't ever get to the very top of the troposphere. We have this nice little video that explains.
Most weather systems occur in the troposphere because it contains 80% of all the gases in the atmosphere, including 90% of all water in the atmosphere in the form of water vapor. Hot air balloons can't fly too high in the air since the gases that keep them afloat can't stay hot enough the higher they go. Not to mention, it's pretty hard to breathe up there.
At the bottom of the stratosphere, fast winds blow in a thin layer of constant air temperature and pressure. These winds will carry you much faster than a balloon can handle, so you'll need an airplane. But as you get higher in the stratosphere, the air gets too thin for standard air travel. Ice crystals will form on airplane windows when you're cruising at high altitudes because the average air temperature at the bottom of the stratosphere is negative 57 degrees Celsius.
A space shuttle is designed to protect its passengers from extreme temperatures. You'd need one to travel through the mesosphere, where the temperatures at the top drop to negative 90 degrees Celsius. The mesosphere is too far away from Earth's surface to be warmed by reflected ultraviolet radiation, and there are few gases to trap heat. Without the protection of a space shuttle, passengers would freeze solid in the mesosphere.
The thermosphere merges with outer space. Temperatures shoot up in the thermosphere because the air is superheated by the sun. Cruising at the top of the thermosphere isn't a problem, since there aren't many superhot air molecules to run into. But a ship can burn up as it returns through the thermosphere. When re-entering the atmosphere, the molecules of superhot air are closer together, making anything moving through them at high speeds scorching hot.
All right, page 4. And I wait and pause and I play the videos. But if you want to turn down my volume and listen to the video on your computer, that way you can see it, that's probably a good idea. So stuck in the middle. A hot air balloon can't climb out of the troposphere, but airplanes can fly into the stratosphere, the second layer of the atmosphere cake. The stratosphere extends from about 15 to nearly 50 kilometers above the Earth's surface, with a layer of ozone stuck neatly in the middle. A molecule of ozone is just 3 atoms of oxygen stuck together. If you've ever been close enough to a lightning bolt to smell it, you are smelling ozone. In the atmosphere, ozone absorbs ultraviolet radiation from the sun. It acts like a natural sunblock. Your mission extends past the stratosphere and into the mesosphere. You'll need to climb aboard a rocket-propelled craft, like the space shuttle, to get that high. Here, molecules are spaced very far apart so that there aren't many oxygen or nitrogen molecules at all. Without many molecules of gas and no special gases like ozone, the mesosphere doesn't hold much heat. It's the coldest layer of the atmosphere. Even though the temperature of the mesosphere is low, it can still generate a lot of heat. Objects coming into the Earth's atmosphere, like meteors and returning spacecraft, can burn up here. Down here. Because there are so many air molecules for the object to bang into, its temperature can rise quickly. The space shuttle has heat shielding to protect it during re-entry, but most meteors entering the Earth's atmosphere burn up here. Page 5. Traveling through the atmosphere layers, you have reached the outermost layer that borders outer space, the thermosphere. There are just a few molecules of nitrogen and oxygen. A thin layer inside the thermosphere is called the ionosphere, which accounts for several interesting phenomena. In the ionosphere, molecules of nitrogen and oxygen, atoms of oxygen, absorb short wavelength energy from the sun and become ionized or charged. The charged ions move, creating an electric current. Just like neon signs glow different colors when electricity runs through them, the sky glows different colors as the ions fly around. We call these vivid, fluctuating colors the northern lights, or the aurora borealis. In addition to producing terrific displays of light, the ionosphere also affects things we listen to. Particularly, at night, it reflects radio waves, allowing radio signals to be heard from far from their origination point. This is why nighttime travelers in Wisconsin can tune into a radio station from Arkansas late at night. There's a couple links on here if you'd like to click on them. The Aurora page is something where they predict the best times to view the Aurora Borealis. So now I'll scroll down here so you can get the stuff on the stratosphere. We talked about that. Pause it to grab that. And the troposphere. Got that. So page 6. Page 6 is to check your understanding. So why don't you go through and click on this and see how you do. You can pause my video and I will see you on page 7. Page 7. To the moon. In discovering the answers to your mission objectives, you traveled up through the layer cake of the Earth's atmosphere, but to see how the layers may have formed, you'll need to travel back in time. You could go back 4 billion years ago or so. You'd be able to see the atmosphere in its primitive state, where nothing could live on Earth except slimy blue-green algae. These simple organisms had a major impact on the composition of the Earth's atmosphere, just like people do today with cars, air conditioners, and other modern conveniences. Geologists travel to ancient landscapes by studying the only thing the Earth leaves behind as evidence of earlier times: rocks. This study of rocks is like taking a trip in a time machine. All right, so we got a video to play. It's a minute and 52 seconds, so if you want to pause your video, you can watch this, get some information from it, and I will see you on the next page when you're finished watching it. All right, so that video talked about how things have changed in the Earth's atmosphere. So the early atmosphere conditions, what were they like? All right, so early in the Earth's history, hydrogen, helium, nitrogen, and carbon dioxide were trapped within rocks and released through volcanic eruptions. So afterwards, some changes were caused by bacteria. Bacteria in the form of algae inhaled CO2 and exhaled oxygen. This increased the amount of oxygen in the atmosphere. Oh, I wrote CO2. That should read O2. So this increase in the amount of oxygen in the atmosphere was called the oxygen revolution. So why do we think this is the case? Well, we found some evidence, such as bacteria fossils are located within rock with bands of iron which had extra oxygen atoms attached. So this was a clue that the bacteria at the time were actually producing oxygen. All right, so now that we're on page 8, we'll talk about what humans are doing and how we affect the atmosphere. In the past 50 years, people have produced chemicals called chlorofluorocarbons, or CFCs, for use in air conditioners and refrigerators. But scientists found that even though CFCs are harmless on the ground, they combine with solar radiation in the stratosphere and break apart ozone molecules. That could be dangerous because ozone is the Earth's natural sunblock. There is no single ozone hole. The ozone layer is diminished worldwide, but it's worse at the North and South poles, where ice sheets reflect more solar radiation back into the stratosphere. Because of the possible dangers, we don't use CFCs anymore. Old refrigeration units can no longer be recharged because CFCs have been banned. So making the connections. In the 90s, scientists in New Zealand noticed that the rate of skin cancers in their country rose dramatically, while ozone layers in the stratosphere decreased. Ozone absorbs ultraviolet radiation, which is thought to cause skin cancer. According to the current theory, less ozone equals more UV radiation, which equals more skin cancer. Ozone depletion in the atmosphere also affects other organisms. Increased ultraviolet radiation in the oceans kills phytoplankton, which are food for many fish. Ocean dwellers aren't the only ones seeing their food supply dwindle. UV radiation also affects the growth of crops on land, which is a threat to our food supply. So for ozone depletion, we've got just about everything will fit on that page right there. So the definition of what CFCs are, how we use them, the effects they have on the atmosphere, and then the human effects. So let's go to page 9. People also change the atmosphere by adding pollutants to the air through their daily activities. Burning wood, coal, gas, or oil to keep warm or cool, and to generate electricity accounts for 36% of all air pollution. Driving an automobile, taking an airplane, or speeding in a motorboat causes 42% of all air pollution. Industrial processes that make things or provide services that we all use to live comfortably lives also contribute to pollution. Air pollution is linked to many serious human health problems and uncounted problems for other animals and plants. Our production of carbon dioxide in particular is thought to contribute to the greenhouse effect. This can lead to dramatic changes in weather, ocean circulation, and rising sea levels, which could be disastrous to coastal cities. People have begun to reduce air pollution and ozone depletion through agreements among nations. In 1987, the United Nations wrote an international agreement called the Montreal Protocol, in which 40 countries promised to cut CFC production by 50%. The Kyoto Accord was designed to reduce greenhouse gas emissions like carbon dioxide. Even though the United States withdrew from the Kyoto Accord in 2004, you can help reduce the amount of carbon dioxide released into the atmosphere by taking public transportation or riding in fuel-efficient cars. All right, page 10. So you've traveled through the layers of the Earth and back in time to see how the atmosphere formed. Because organisms interact with it and change it, the future of the atmosphere is up to you. All right, so at the bottom, we've got a little review for you to do. You can just click through it. Talks about each layer of the atmosphere and the things we learned about. And the final page is just a little ending page. And that's how all these studies are. So I hope this helped you out. I hope seeing the study guide being filled out will help you on the quiz if you still need to take the quiz, or if you have already taken the quiz, you can always go back if your grade was not satisfactory and ask your first period teacher to reset it for you. Please let me know if you have any questions, and I will talk to you again in the next study guide.